place where you initial say, yes, I did open the gate or whatever the function was, and I really like to put the hour down that I did that at 10:30. Because you can't remember. Even an hour later, you think, who did that, and did they really do it? And people can do anything, but they don't always do everything well. So the checklist is a very important part of switching. It doesn't sound like high-class engineering. It isn't, but you're working with people. Remember that you're protecting people's lives and your own. Because I'm the lecturer, I can assume anything I want, so I'm assuming that everything has been done perfectly and I have no problem. That makes life easy for me. And that's where we're going to progress from that point and see whether or not that indeed is true. Now, as electrical engineers, you think, well, we've got volts and amps and conductors and things that we're familiar with. That isn't everything. There are other sources of energy, and there are other sources and techniques of switching and mechanical devices. The familiar key interlock that you've got, two breakers and a tie breaker, and you have two keys. You can only close two at any one time because you do not wish to parallel. Or you have a sequence, and until you take the key, open this breaker, take the key out, put it in that breaker and close it. You can't. It's a very effective system. It doesn't show up on the one line. It's not electrical. So you must find a way, when you develop your switching, either by notes or whatever works for your system and you personally, is to say, in addition to the electrical components, we do have key interlocks, and they function in this fashion. Because you will be, in your instructions, will say, close this breaker, take the key out, whatever you're supposed to do. Another, oops. Am I back online? I think so. There, that's better. The grounding cables, if you're going to work on a bus, you want to be sure that you are not the path from the bus to ground. No way. So the thing to do is to get a grounding cable, fasten one end securely to earth, and then the other three wires or whatever it is, you clamp on or bolt on the buses. First, you have to have it in the instructions that after the bus is de-energized and after you test to be sure there is no voltage that you didn't know about, then you put on the grounding conductors in a certain fashion. And then don't forget that toward the end of it you say, now that we're finished, remember to take the grounding connectors off the bus before we energize it. It doesn't always happen. And that's why I like a checklist that I thought somebody put the grounding connectors on, and maybe they put a tag on, but anyway, they put it on. And I want to know at the end of the job that somebody took it off and said they took it off. And I would really like to have two people, so I take it off and put it down. You watch and make certain that I did it right and didn't make a mistake. People are people, they make mistakes, not on purpose, and not through carelessness, but because we're human. Draw breakers, that's another disconnect device. That you open the breaker and then you can pull it out. Well, pulling it out isn't an electrical function, but you need to know about it. So there's several things like that. I like to have those things written on the one line that I'm working with. It makes the single line a little bit messy, but the information is there. And remember, the single line is not a work of art for your own glory. It's a working document for the people who operate the system. So if it helps the system, it's a good addition. If it doesn't help them, then it's probably not necessary. Those are all the other things you have to think about. One thing that, think about springs. Some of these breakers and equipment have heavy-duty springs, and if you trip the breaker and then the spring operates it, That's a tremendous mechanical force. You can smash your fingers or do other things. So think it through carefully, and if it's at all possible, get somebody to follow after you to make sure that you got everything. Well, now we did pretty well. Already we know everything about the system except what we want to do. So then you have to define what is the scope of work. You're going to work on a particular bus, or a particular motor, or a particular transformer, or several of them, and you're going to change something. Are you going to clean it, or are you going to move conductors from one place to another? Then you have to think, why am I doing this? Is it necessary? Is it wise? Is it prudent? The problem comes, and this is a matter of personal relationships, that some manager says, I want this done. And you are the newly hired junior electrical engineer, and you look at it and say, this doesn't seem right. Now you've got to talk to the boss and say, boss, I think you don't know what you're talking about. Be discreet. But you have to do it. That's why you have the jobs, so you help them. They don't know electrical, or you wouldn't be there. But you do know electrical, and they really count on you to say, in my opinion, my professional opinion, this would be better done a different way, or it's not wise to do it this way, for some reasons. Something will break, something will get hurt, or whatever the reason may be, and they may be a little annoyed about it, but they are appreciative. There's only one time in my whole life that I had to tell somebody something they didn't like. And many times I told them what they didn't like, but that's the way the system is. But there was one sawmill in my hometown, and I was working on a synchronous motor. They wanted to, I can't remember. We were doing something with a synchronous motor, moving it or changing it. And when I went into the plant, I went by some switchgear, some substation, transformers. You could reach out and touch the bus. It was there. And I wouldn't touch it. I knew that was not a good idea. But the workers around there didn't know. They were just cleaning up sawdust and moving whatever they do in a sawmill. So I told the owner, I said, I'll do whatever on the motor, but you realize you have a very hazardous thing here. Someone could get killed. You need to put up a barrier, or you have to do something. And he said, no, I won't. And he was quite insistent upon it. So I said, well, I told you, and it's, I'm going to send it in a note, and when I get my report, I'm going to say, and you have this dangerous situation. And that was the end of that. I was consulting, like, hey, a little while later, a few months later, they said, well, we have some more electrical changes. Come into the plant and give us instruction. I said, if I come into the plant, I'm going to see that same hazard. I'm going to give another report, and this time I may have to report it to the authorities. So he said, well, then don't come in, I'll find somebody else. So he was getting ready to sell the plant, he didn't want to spend any money, but that sometimes it will happen. So I didn't get paid for that job. I didn't do it neither. And I don't blame them, I don't agree with them, but you will run into those situations. It's hard to be tactful when sometimes you have to be blunt. I've not always been very good at that. Now you have to start developing the switching program. You know everything about the system, you know why they're doing it, you have all the information, you know the schedule, it has to, everything you need to know. We finally get around to the purpose of this is to talk about the switching. I don't want to miss So you go to the single line, single line is the key to the whole operation. And you look at that, get a good copy, and look at it and say, what do I need to switch? Highlight that or mark it somehow so you know what it is that you want to work on, a particular bus, whatever it may be. What I like to do, I think it's essential. What is the present condition? And you have the whole power program or the data. What is the load flow now? Is this bus overloaded, or is it, are the bars, huge bars and few watts, or vice versa? Is the voltage bad? Maybe it should be at 98% and it's at 89%. Is a short circuit level? What is the short circuit level? Is it dangerous? Do I dare go close to it? Maybe it will blow up just like that. So you need to look, what is the present condition before I start switching? Where am I now? What am I starting from? Don't let me jump into it and I don't even know where I am. And here's where, if you purchased a software with a switching program, I guess all you do is put a switch and it comes up with 1,000 different choices and some are acceptable or not. I don't like doing that. I like to look at it and say, it can't be that complicated. And the operators, the electricians, or whoever's working on it, it won't be me. They have to live with it. They're not going to have all this information. So I look at it and say, what's the first switch that I would like to open? Probably from the power source. And on the computer program, I'll open the switch. Now, or close the switch, whatever it is. And that's a judgment call. If it's wrong, it's wrong. You make another judgment call. And then stop and say, step number one was to operate this switch. What did I do to all of the measurements that I had before? Of course I must have changed it. Probably I've changed it. Did I make them better or worse? Did I make them dangerous? And I still provide, will the system still work when I operate that first breaker? Is anything that was running at 80% now at 101% or 99%? If it is, I'm going to be nervous. If it's 150%, of course, you can't do it. And then decide if you can take the risk. Or should you do something to provide protection during the switching? This question of decide if this is an acceptable possibility. This is a new bus that was installed in 2011, yes, on a military base in Alaska at 480 volt, and they have a big station service bus for a powerhouse, another big station service bus, and some transformers feeding it and loads, and they're critical. You don't want to lose the power to a point. And they have a tie breaker in between, so if this bus is de-energized, you can close the tie and feed it from the other. The system is adequate to do it. What they want to do, and they claim it's very important for their operation, particularly in the wintertime when it's cold, if they have power coming on this bus and power coming on that bus, they want to close the breaker, parallel the two buses, and then open one. And then they transfer the load without any loss of power, and everything keeps running. That's a valid operating condition. However, when we come in, originally, the bus is rated, I'm trying to remember, 42,000 amperes, racing and short circuit and everything else. And the actual condition was something like 36 or 37,000 amperes. Well, 36 or 37 is comfortably below 42, so it's no problem. However, when you close the tie breaker and you have two sources feeding it, the short circuit duty is something more than 60,000 amperes. Well, more than 60 is a lot more than 42. If anything happens, when you close the breaker has to trip with 60-something thousand amperes. It can't do it. So the arc will persist. The breaker may open, but the arc will persist. And the energy, we're talking, let's say 60,000 amperes. The energy is I squared, so it's a tremendous amount of energy in a little cubicle, or about that wide. It's going to explode. Someone will get hurt, and you'll ruin it. I talked to the manager of the water house, and I said, Marty, you can't do this. I said, well, that's what the person who designed it told me. He said, you can't do this, but I have to do it. I said, someone's going to get hurt. They'll be there in the break and push the button and the thing will blow up and kill them. And he said, well, what can I do? He said, I don't think it'll blow up. I don't think we will have a short circuit. That's a judgment call. It's his judgment. He's probably right. You know, the probability is very small. The risk is very large. And he said, well, what can I do? I said, if you're willing to take the risk that the system may blow up and you'll lose power, if you can live with that, now the question is, how do you do the switching so you don't kill the person who does the switching? And that's basically what it comes down to. What we concluded was, and this is not a new technique, but we finally said, okay, you will operate to close the breaker for just a minute until we get these things going. But you do it remotely, so if the breaker is over there, I'll be standing back behind something here and push the open or close button, and of course the forces they go down as a square of the distance or something. Anyway, I'm safer. I may be scared to death when it goes up, but I won't die. So those are the things. Is it acceptable? The risk acceptable? And the manager said, yes, the risk is acceptable as far as operation is concerned. Is the risk acceptable as far as danger to the electrician is concerned? He said, no, it is not. So we found a way, and then we said, and we will have people to keep everybody else in so somebody doesn't accidentally walk by. Those are judgment calls that you as an electrical engineer have to raise to the surface and present to the people who are using electricity, and they're not easy. What's a poor man going to do? He can't shut down the boilers when it's 40 below zero outside, and they're counting on the steam to keep the place warm. And he can't not do his maintenance, or he won't have anything. So it's all. There are ways to change the relay settings, and if you look in our class, you'll see temporarily I can make better protection so we have less hazard, trip the breaker sooner. The bottom item is one that's real important to me. You go through and try several things, and some of them work and some of them don't, kind of. And then you think, I wonder, did I check that one? I can't remember. So whatever you do, if it's a bad result, file it. And if it's a good result, file it. So when you come back in 3 or 4 hours a day, I'll go in the file, I think I did that. You don't have to do it again. Otherwise you go round and around and you're tired. Any unexpected interruptions to power, that's always the thing. If you're working on this particular portion of the system, everyone's prepared and everyone's happy, and for some reason that you never thought, another load off in the distance was interrupted or failed to get power. Because you didn't think or didn't understand that they were using the power too. And this is where the single line comes in. These are all very annoying problems when you're doing, and it comes down to working with people. And a lot of people, electricians will say, we've always done it this way, we've never had a problem. That may be so. But look at the system and see if there's an inherent possibility of a problem so you can avoid it, or alert people saying there's a possibility that something untoward will happen, something you don't like. Don't calculate by hand, it takes too long, it's not accurate, and it's a real pain. Now, how do the software programs work? You will have I'm assuming, and it's a pretty safe assumption, that your software will say, if you have equipment, you will have the rating on it, it'll say this bus is 42,000 amperes. If the short circuit level exceeds 42,000 amperes, then it turns red or something you can see immediately, I have a problem. You can also set the software programs, if you choose not to go to 42,000, that you think 90% of that, 38,000 would be plenty. Then you can set the limit at 38,000 so that if the short circuit level exceeds 38,000, you'll be alerted. If it goes to 39, you may say, oh, it's 42, that's all right. If it goes to 59, you'll say, it's not all right. So you will set the limits inherently in your single line, and you can change things around in the software. That's a blessing of the software. You can see what happens if you do something without actually doing it with equipment and finding out the hard way. And more, keep track of it. You keep good notes. You finally got through the first one, and you finally decided, I can live with the first operation. Now try the second operation, which is maybe probably for, and on. And you keep going through the steps, one step at a time. Don't jump ahead and say, well, I'll open 3 breakers. You don't open 3 breakers, you open 1 and 2 and 3, and see at each step what the impact is on the system. Go like this tie bus in the boiler house. You're going to close 1 breaker and open the other. It's only 2 operations. It wasn't 1 operation, I'll close and open. It was 1 operation, I'll close high, or have an extremely high short circuit, and then I'll open the other one and I'll have normal short circuit. So you would have to go through those very deliberately. Well, you know all that. And you keep doing it again and again and again until you're satisfied that, yes, I have it may not be a perfect switching system, but I have a safe working system that will do the job that has to be done. You don't have to be perfect, but you have to be successful. Now, I would like to go on and demonstrate. But do you have any questions? I've been up here talking, and have I said anything that was worth listening to? I've sounded like this, or I wonder why I came. But that's a safe assumption that, yes, you have all the background of the calculations, at least more or less, or you can find you're comfortable. I think. Yeah. Okay, you're comfortable. One nod is all I need on reassuring. The other thing, how do you feel about switching? If you have the task, you've just been transferred to a firm or something, and they ask you to do some switching. You're not too familiar with the system because you're new. It is a great responsibility because you're talking about people's lives. People get killed, or they get badly injured, and then sometimes you think that's even worse. But you feel that you'd be willing to do that, given enough information, not just go out and do it, but would you be comfortable doing that and dealing with that? You would not. I don't blame you. It's not easy, and it can be the personal side is the hard part. We know electricity. There's no problem in figuring. Well, it's a problem. It's not beyond us to calculate and figure out what will happen, what we would like to do. But you're working with people who have a production line. One situation, they had, I think it was 5 production lines. We had to shut down one because the system would be overloaded. So we said, well, shut down this production line. Well, you can imagine what the manager said. He was just screaming. He said, shut down somebody else because I'm so important, and they need a big argument. So it was out. I said, okay, we'll shut down this one. It didn't get any better. And he said, well, you have to shut down something. And the answer was, well, you confounded electrical engineers. All your engineers are the same. You won't let us do production. Who do you think is making the money in this company? And on and on. So, and I didn't like it. I don't blame it. So what we ended up doing is I went to the plant manager and I said, plant manager, I got 5 enemies. And one of them is going to go down and he's going to be a big enemy. The others will be suspicious. Which one do you want to shut down? It's the plant manager's job. It's my job to tell him. It's his job to decide. And he said, when do you want to do this? And I said, Saturday. And he said, well, on Saturday, shut down this one. How long is it going to be? 6 hours. Can you do it in 6 hours? Maybe. Can you do it in 8 hours? Oh, yes, in 8 hours. Okay, you can shut this one down for 8 hours on Saturday, from 8 in the morning until 8 hours hence. And he's a manager. That was his decision, and he's responsible for production. But he needed to know, and he needed to be told, and the managers of the department needed to know that they had the directive and the support of the manager that if there's no production, it's because he said, shut it down. And those are things you have to know the process of the electricity is serving. Nobody wants electricity. They want light, or they want heat, or they want air conditioning, or they want motor to turn. They don't want electricity. It's an expense. They don't look kindly at it, and you're added another expense. You're not making a product we can sell. On the other hand, if they don't have it, they won't sell any product. They won't have any. And they know that. But the personal relationship is very, very important. And I know the concern about how do you do it. It's a matter of diplomacy. I don't know how to describe that. You know, you're working with people, and everyone's different, and different days they're different. That is important. Why are we even sitting here talking about a computerized program? Because you can check a multitude of possibilities very, very quickly and accurately. And if you do something that's a sudden change, a step change, or you're changing a bus, it will respond immediately. The information you get back will be fact, not expectation or estimates. And you will have a record, so if you come back or if somebody else comes back a year or two in the future, they can say, well, this is what they did when they had the event 2 years ago, and as we recall, there were some problems here that they were unexpected. We should look at that, and the rest of it went pretty well. That's important. Don't do one part of the system one way and another part the other way. It's too hard to keep track. It's too hard for other people to follow. And your level of understanding is up here, and theirs is down here or down there or down there. So you have to make it as easy for them to understand as possible, and make it easy for them to trust you and have confidence in your judgment. Where are the problems? I almost always, unless there's some reason I cannot do it, if I have a group of electricians or workers, some electricians, some not, I want to go over the program with the foreman or the leaders, the key people beforehand, and say, this is what I intend to do. This is my program. What do you think? And they're working closely with it. First, they will understand then what you're trying to do, and second, they may have some information that you didn't know about, and that's important. Maybe they'll say, we had trouble with this feeder, and we've taken it out of service, and we just have a piece of temporary wiring now. Well, that wasn't on a single line, and we're going to change it, first opportunity. There are things like that. Also, what I'd like to do, and this is teaching. If you're teaching, you say, this is the program. We're going to do this, and this is your portion of it, and that's what you have to do. And the gentleman nods and says, yes, I understand. Thank you for explaining it. And say, no, tell me exactly what are you going to do? And the answer that comes back will not be the information you gave him. Probably because you were not clear, probably because there's too much to understand, and probably he wasn't paying attention. So you go back and forth until you're satisfied and say, okay, now you understand, I want you to do 1, 2, 3. What are you going to do? And he said, I'm going to do 1, 2, 3. I got by that one. But you have to work with your team members, and it takes time to do that. So when you're planning your job, make sure that there's at least some time programmed where you can go over to people to make sure they understand what you want to do. And the other thing is it establishes confidence in you. They know that if they don't know everything, at least you understand that they can come to you for help. If something goes wrong, which it will, they can come to you and say, something went wrong, what shall I do now? And feel confident that you will answer them safely and well. If you have to change the program, and you do change programs, talk it over with the people and say, I have to change the program, this is a change I'm going to make, and this is how it affects you, what do you think? And listen to them. Why should we bother with all this? It sounds like a lot of work. It is a lot of work. It really saves time. It does save money. You don't blow up equipment or hurt people. And you have a program so the work proceeds methodically and gets done. To keep people from getting injured or killed, and you can say, this is how this system will perform before, during, and after. It may be better, it may be worse, it may be acceptable, it may be marginal, but that it will be the performance. Yeah, but was it worth coming here? And I presented this for more or less 4 hours in Hyderabad, and it was a different group of engineers, and a lot of them were practicing, and afterwards the teacher came to me and said, Erling, we spent too much time fooling around with the one line and showing the example. Spend less time on it because, how many times do you have to say the same thing? So that was his very pointed suggestion and very good one. We've known each other for a long time. And that is, and part of the reason why it was so acceptable, we've known each other through Ieee-Ias for many years, and yes, we criticize each other, but it's constructive criticism. It's not saying you're stupid. It's saying you made a mistake, and I think you could do better. And here's an approach. And a world of difference. A world of difference. So where we stand now is that we know all about electrical calculations. We know why we're switching. We know what we have to do. If we're going to do a switching program, where do we start? How do we proceed? Where do we end up? So that, in the past hour, we've learned all that. We've learned about all of the hazards. Somebody might get hurt or it might go on. We know all of the benefits that will keep the system going. We're going to do our best. And we're all very cognizant and aware of it. We'll have to deal with people who will be difficult at times, and you have to deal with them patiently. You have to be patient because if it's a piece of machinery, moving machinery, you can look at it and say, I can see that that's turning. But if you talk to them about electricity, you say, well, that bus is energized and that one is not. It looks the same to me. I can't see electricity. And that bridging that gap is real important. And it really comes down to a matter of confidence that the person who's looking at it says, I don't know anything about electricity. I don't want to learn anything about electricity. I will trust the electrical engineer with my life. And it is a responsibility, but it's an opportunity to be blessed in being able to have this education, and we need to pay it back and make good use of it. Oh, that's the end of it. So what time is it now? Is it? Can we break now for tea, or do I have to keep talking?
We don't have some questions we can ask. In astrology, in Indian astrology, we have this pattern that your birth chart may be affected by immediate star. Immediate stars. The person who's looking into your horoscope may be only looking into the effect of the immediate stars around your birth star.
Yeah.
But there might be the effect from faraway stars, which may be more relevant or at that time. And you are going to get affected in a different way. Maybe. And this person would have predicted in a different way. Like that, when you were talking about the switching and the guidelines, I was thinking, as a person who thinks what way you should program and check,
Yes.
At that time, what all priorities do you look into? Of course, there are relays trips and other things. But, for example, there's such things as residence
Yes.
or something. You have to look into a huge effect back then. So,
Correct.
how do you prioritize these things and take the somewhat okay through them? Each time, do you think all these effects every time? Or
You're quite correct. And how do I know? Is my answer I don't know. That's the problem. I'm sorry you asked the question. No. No, that's right to the point of the whole thing. That what is the broad effect, and how do you know what is important and what is not important? And the other thing is that once you decide what is important at the beginning, let's just jump ahead a bit, and you're correct that you're fallible. In the middle of the switching, something will happen, and the importance is changed. And now, at a moment's notice, you have to change the priorities. And I have difficulty with that. I don't like doing a job and planning it in the morning and doing it in the afternoon because my mind doesn't work that way. Some people are quick, I'm not. So what I'd like to do is plan the job today and say, well, this is for Monday. Let me think about it over the weekend. Or the next morning you wake up and think, I forgot about that. And not everybody's that way, but I think I have great difficulty analyzing this and coming to a conclusion and accepting it because I have mistakes in it. And setting the priorities is really difficult. I guess my approach now that you ask is you look at the analysis and say, this is what it will do to the performance of the system. Then you look at the user, the system user, and say, which jobs or which areas of power service are not important. The lighting for the street. If the lights go out, be careful where you walk. You look at the pump for pumping water. Well, there's water in the tank. You can go for a couple of hours. And then you may find some things that are very, very critical that you dare not turn the power off. And you say, well that's a priority that I must keep the power. I ran into this one, and it ended up as a legal case. It was a copper mine in Nevada, and they had a bus, 2,300 volt bus. It was Delta system ungrounded, and they fed it from two ends. It was disconnect switch at each end, and some 2,300 volt motor starters, and a man got injured because it was energized. That's another story. But I said, why didn't you turn the power off? And they said, we can't. And I said, well, why can't you? You have a breaker. And they said, no, because, and this is the priority, they said, this bus is serving some fans for ventilation. If we don't ventilate the mine, the people will suffocate. And we can go a little while, I forget how long, but not very long. And also, this bus serves several pumps that are pumping water out of the mine where it seeps in. If we don't pump the water out, the mine will flood, and we will never be able to pump the water out, and that'll be the end of the mine. That's why it's critical. So that was not my priority, because I didn't understand. And you really have to look at the operation, and you may have to challenge them and say, are you sure it's that important? It doesn't look that important to me. Is there some other way we can manage it? That's a hard question.
Sharing.
Basically sharing, you're quite right. You have to talk to people, and it's not always easy for engineers to talk to people, especially people who don't understand electrical. But you have to do it. You work at it and learn.
And especially when we teach power system basics and when we talk about resonance, that is the time when I understand the graveness of the situation. That effect may come from faraway places where the tie line is there. And how do you control or make a guess of what is going to happen next instance when you switch over? Then this is the thing. Then I grasp the graveness of the situation, and then I hope that students don't ask, what do you do? Because I need to know a person who has already done
some of the power companies worry about that with the, what is it, distributed generation, whatever the word is. I have a generator at my end of the line, but I get most of my power from the power company. So if the power company, or maybe I have a photovoltaic cell or windmill or something, if the power company goes down and loses power, I'll turn on my own power. If the breakers are not open properly, I will energize their line, and they think they have a dead line, but I'm energizing it. Maybe a small generator, but maybe a high voltage. So when you're at risk of something like that, if you say there's something bad out in the jungle, put up a fence. And maybe you don't need it, but if you don't know, maybe you do need it. You know, that's one of the remote things that can affect you. You don't know. The problem is we don't know everything we need to know when we operate a system. We know much of it, but not all of it.
It's like crossing fingers.
Yeah, well, maybe you say a prayer. Anyone else? That was a good point. That is very much to the point. I'm glad. That's good. It's hard to think of all these things. So you're all set to go off and now do some switching? You work a scenario that you individually or we as a group are recent hires for a firm. We're the electrical engineers, and then the senior electrical engineer says, we need to do some switching. There's one line, we'll go through it and see step by step. What do you think about the whole thing? And what would you do? What would you do? Here's the one line. Oh, this is the software I use, and I don't know how to read it, but that says stability. This says power flow. This says coordination. This says short circuit. This says database entry, and some zooms and some other things. And so you can do all of the programs you want with this. Now, for this simple one line, I made a little one line. And I'm only going to go through load flow because it's easy. I had to pick one. I picked load flow. If you were going to do this study, you would look at what is a load flow and what are those other things, the power flow, the short circuit, and the others, the stability, whatever you need. Let's assume if we get load flow, somehow magically we did everything else. So the old engineer gave you this one line and said, take a look at this one line and spend a day or two studying it because we have some switching to do, and what do you think? And basically, without going into detail, up at the top there are two transformers, and you can't see it there, but there's a 69 kV line that feeds it. That's the number I chose. Well, that looks reasonable. And they're rated 20 MVA each. Well, that for an industrial plant, I guess that's okay. Each one feeds a low voltage bus. I picked 13.8. I had to pick something. I picked 13.8. And that works out fine. That sounds reasonable. And then you look at it, it gets a little complicated. And you look over here, and there's a generator, a 10 MVA generator going up in the 13.8. That sounds right. And next to it, why am I going from right to left? Because the right side looks easier. I want to do the easy part first, and I don't want to start on the hard part. So I look at that for a while, and I say, well, there's an induction, a synchronous motor there. Hoop-up. There's my sister's family, and there's a load that goes down. There's another transformer. And then you see there are a couple more transformers and some loads. Those are adjustable frequency drives. They may be a problem, I don't know. And you get over toward the middle and you see some more buses. Then you begin to see that there's over on the far left there's one with a tie breaker. Tie breaker means it's a little more complicated than you might wish. Well, that's the way it is. And you get down at the bottom, and the old engineer told you, he said, no, these three bottom buses are critical. And you'll notice they're tied together, so if we lose power in one, we have a second source, because we have to keep those things running. and they're fed by two or three transformers. So you look at it and say, well, that looks like a reasonable system, and it's working. Now they have some problems, but it looks fairly decent. So you're satisfied that you've got a single line that seems to work. So let's see what the power flow looks like. So let me get this on power flow, and then it says solve. So I go over where it says solve. And I have to zoom in because you can't see the small print. And we get the zoom in here, see what we're doing. And you say, wait a minute. We're not supposed to have red lines on the operating system. Red means bad. And we can look at it, we can get a little bit bigger, just to pick an example. And down here it says it's 0.398 of the base of the amps on watts, and then something else on bars. And if you look at it some more, and you say, I can't read this drawing. Look, things are written on top of everything else. So you say, well, maybe it's better someplace else. So go up where it doesn't look any better there. There are too many trouble areas. And you start looking at them one at a time, and you say, what do you say when, that's my question. Okay, now the chief electrical engineer says, here's my one line, I've been running with this for 15 years, it's pretty good, and maybe a couple things out of date, and you get this, and there's red all over it. What are you going to do? You completed the class an hour ago, so you must know. What would you do? What would you do if I were the boss and I said, hey, junior engineer, take a look at the underline, it's pretty good. And you look at it and you look at it and you say, no, it's not pretty good, it's pretty bad. Now you've got to talk to me. What would you say? It's not easy, you know. Yes, what would you say? Don't insult me because I'm the boss. What do you have to say? Somehow you have to say, the single line you gave me is not adequate, it's wrong. You have to do that tactfully because you don't want to lose your job. But, there's my, you don't say that. Thank you. Somehow you have to say, I'm sorry, sir, but the single line you gave me, say some flattering things, as much of it's very good, but it's wrong. I need to go in and investigate and get all of these things right. And being the boss, I'll say, well, we have to do this next week. I can't wait for you to fiddle around with the single line. We've got some switching to do. What do you do then when I'm just not being cooperative? And you say, we really need to do it. You have a valid reason. I'm an engineer, I understand, but I don't agree. And I say, we don't have the time. What are you going to do? And that's a crucial part. And like you say, that's not all fun. But what would you do if I gave you that and you said it's wrong, it needs to be fixed, I'm afraid to switch with that because the whole thing, I don't know what to do. I'll kill somebody. And I say, well, we're in a hurry. We can't wait. That is difficult. It's really, really difficult. And there is no good answer of what you do. There's no predetermined answer. You have to use your judgment and your tact and your understanding of people and say, well, maybe we can look at something. If the system is working, it can't be all of that. Probably the data is wrong. Why don't you let me look at some of the critical areas? And anyway, which part is it that you want to switch? You're not going to switch the whole thing. And he said, well, the first thing we're going to switch are those two buses you see there. And he said, well, how would it be if I focus on those two buses and get the data correct, and we assume that the rest of the system works, even though we know it doesn't, even though the data is wrong. And then after this switching operation next month, I will go in and correct the single line. you may have to do that. You have to be reasonable. The man has a job to do. The plant's going to be shut down for the switching or whatever. And time runs out, like final exams. You say, I'm not ready. If you would give me an extra week, I'd be ready for the finals. I'm not going to get an extra week. And that's the way it is. So there we have a single line, and I know it's bad because I made it myself. And look at it and see how bad is bad. And well, let's say we go over and just, not because we're too interested, but here's a generator. Oh my goodness, we didn't see this generator before. And it's, here's one, generator 2. I wonder what generator 2 is. I can't remember. Well, if you have a database, it'll say there's generator 2, and it's on a particular bus, and you have the information is used for swing, so okay, you know that. You say, well, here's a load that's going pretty good. There's 11.299 kilowatts going down, and 0.85 megabars. I wonder about that cable. Oops, I got the generator instead. So you can look at things and say, come on. I can't even get my data to come up. Isn't that terrible? And you know, you can go to your system and find out what are the conductors, what information has been entered. So let's assume now that the poor man who's desperate with the new engineer said, well, all right, fix up as much as you can and we'll do our switching. Now you go back to old engineer and say, exactly which buses did you want to switch? He said, well, things have changed. You see those two purple ones in the middle? Those are the ones, no, I'm sorry, you see these, you get this size where I can see. That's when the old engineer complains about his glasses. But so you see these two buses here. We have to turn the power off and work on them tomorrow. You give me some instructions so I know what to do, and make sure that what you decide is going to be safe. And you say, certainly, sir, we got to. And there we are, the buses. Let's get them on the so we can see them. That's about big. Can you more or less see what they are? I'll assume that you can see what they are. Okay, here's my question. Since I'm the old engineer, don't have to do it. What are you going to do? What's the first operation you're going to do in this switching? On any part of it. And you can do it on a computer. If you make a mistake, nothing blows up. So, at working on the computer, as you go back to your office and start working on it, what are you going to try first? You have to switch something because we want to work on this bus and we want to work on this bus. The first thing to do is look at where does the power come from? Well, there's a transformer and the power comes from this bus, which is 13.8. And the other one comes from the same bus. Interesting, but that's just the way it is. The buses have names. This is 7, this is 8, and this is transformer 9, and so on, and they have ratings on them. The little aside, all of the transformers here are solidly grounded neutral, but they're not double. And the reason is because I didn't want to put in all the neutral resistors. So one of the first things you look at, and I would say if you're doing it, keep notes and say, number one, that they're all solidly grounded neutral, which means if you get a line to neutral ground, there's no impedance in the neutral, and you'll have a very, very high fault current. That's not wise. You may be stuck with it. So write yourself a little note saying, or put it in the computer in the file and say, I want to check all of these solidly grounded neutral transformers. Why did they do it, and should they be changed? So that you save that as you look at the one line, because otherwise you'll forget. So write it down. You're suspicious of the solidly grounded neutral transformers, and you're stuck with them because you can't change it now. But that doesn't mean you have to accept. Well, we still have the problem. What do you want me to do for these two buses? I know what you're saying. You want to open this breaker, and that breaker, there it's open, and you look at it and you say it doesn't have a name. It's on bus 2, and we have a lot of information. That's very interesting. And you think, well, now the reason I want to open that breaker is to stop the flow of power, load flow. So you go to power flow. Okay, let's look at power flow. And what is the power flow in that bus? I'm going to solve and see what it says. And when it solves, this one says, let me get this bigger so you can read it yourself. Can you read that better? No. That's the butts and bars. We work in vectors. And you can see that there's twice as much power going on the left one as in the right one. You didn't get it. You cleaned up the first transformer so you can read the information. You didn't get around to fixing the one line on the second one. And that's what happens. This is, well, there are two reasons why I did it this way. One is I didn't have enough time to fix it. And the other is you wouldn't know how to fix it if you didn't do it yourself. So that's my excuse is this is so you can see what is to be done. But you look at these things and you say, it's 13.8 and 0.48, I can read that, and I got some information. Write yourself a note, I've got to clean up the drawing in that area, it's a mess. And you look at this one, and you say, oh, I can read that, 1, 2, 3, 4, a little bit overlap there, but that's all right. So, now we know the load flow, and what happens if I open this breaker? It's open. Well, what do you know? There's no load there. Well, that's a good sign. That's what you wanted. So you say, I'll write that down or keep a record. The first thing I'm going to do is open that particular breaker. That will kill that bus. And yep, the entire bus is dead. There's no power flow there. We're running a switching program. We've got the power turned off that breaker. What's the next thing they're going to do? What's the next thing you think you should do? Or that you might do? Somebody take a guess. It doesn't have to be right. If it's wrong, it'll show up red and we'll change it. We won't use your name. But the next thing, you write that down. Number 1, open that breaker. Number 2 is probably put a lock on it and tag it out so nobody closes it while you're working on the bus. So number 2, you say, lock it out and tag it out. You're going to put a lock on it, whoever's in charge, whoever's working on it, and you write a tag on it and say, I'm working on this, so they can find you if they need you. You may want to look at the breaker and say, that's a 13.8 kV breaker, 15 kV plus, so you know it's on wheels and you can pull it out. So the next step you may say, withdraw the breaker. So now you've got open air so that you know there's no hole of the breaker that happens to be stuck in or anything like that. It's really an open circuit. And you may have something and say, and take the breaker to the shop and maintain it to make sure it works. That sort of thing, if that's part of the job. Now, is that bus safe to work on? I think so. Are you willing to test it for me and see if it's hot? I don't think so. So you have to go through these things deliberately and say, I'm pretty sure. I know I opened that breaker. I know I've withdrawn it. I know I got the people who are working on it to put their locks on it so it doesn't accidentally get closed again. But there may be an induced charge. I may have made a mistake. It may be wired up wrong. Somebody did something and nobody knew about it, or something failed. Well, things go wrong. So what do you do in case something goes wrong? You say, first thing I'm going to do, I think I better put a ground on that. I'll connect one end to earth. So you have to take a voltmeter, voltage probe, and do it with somebody who's properly dressed so if there is a flashing you get burned. And you test the voltage. Well, first you test it to see if the meter is working. You test it somewhere and it says, yes, 13.8 kV, okay, it works. And you test it here, and it says 0, or maybe it says 2 or 3 or something. Basically 0. You say, it's dead, I'm glad. And you go back and test your meter again. Maybe the meter broke when you went from here to there, and it read 0 because it was broken. You go back, and it's still reading 13.8. I'm confident that the meter was correct all the time from when I first tested it, I tested the bus, I tested it, so that really is the de-energized bus. And the next step then is put on the ground clamps and write it down somewhere, get somebody to initial it that I put it on, and make sure it's in your sequence that sooner or later you're going to take it off before you close the breaker. So we got that bus all looked after, and we've done all our maintenance, and we're finished, and everyone's happy. And said, thanks for doing it. You're a better young engineer than I thought you were. So he said, how about the next bus? And you say, well, okay, I'm going to try the same thing. There you are, you open the next bus, and you have the same thing. You've gone through it, you're done. So you say, well, let's close this one. And there you are, it's energized, and you bring the volts up, however you do it. And, oops, there you go, that one closed, and you're back in operation. You decided which breaker you wanted to open, what switching you wanted to do, how you wanted to do it, who you wanted to do it, how you're going to test actually during the operation to make sure that your decisions were correct. They may have seemed correct, they may not be correct, but you be very suspicious about the system and about your work. And then at the end, you took off all the grounds to be energized, and everyone's happy the job is done. So the next job, they say, well, there we go. You see this bus here, we have to work on that. It's a little more complicated. And remember that on that bus down there, somehow there's a feed that comes down and serves this. Remember, this is a critical bus, young engineer, so don't lose power. I can lose it for a minute, but I need power there. So make sure you look after that. And you say, okay, hey, I'm pretty good, that's no problem. There we go. I can't find it. There we go. Did that first switching operation make sense to you? Did it sound reasonable? Is that generally what you might try doing? Or it doesn't have to be perfect, but was it good enough or pretty good? I think so because I did it. That doesn't mean it's correct. Well, nobody's arguing, so I say, well, the first operation, when those two buses, we took them in sequence, nothing happened. At least it was acceptable. Maybe next time we'll think of a better way, but that one wasn't too bad. Now let's see what's going on with this other bus. There's my cursor. There's the bus we're looking at. And here we are. Let's make it a little bigger. And we have the same complaint that it's kind of a messy drawing. So you write yourself a note that said, well, there are no red lines on it, but it certainly could be a lot better. So you write yourself a note that when I get the time, I'm going to make that better. So I just don't like it. Let's make it a little bit bigger, and then I'm going to ask you, which breaker am I going to open? Apparently, we turn off power. We like to turn off breakers. Well, you were looking at these two buses, and they're, what shall I turn off? You pointed with two fingers. I don't know which one pointed. I was watching. Well, it's pretty clear that if this is our source of power from the utility, this is the breaker I want to turn off. And it looks like a lot of power goes down there. None of it's in red, so I guess we're all right. Let's take a chance. There we are. Hey, I turned the power off. Does that look reasonably safe now? Yeah, it does. It is. It is. You can work on it. We don't need to know that red one because that's not part of my job. We ran into a problem. The feed all the way down here, bus number 12, down at the bottom, and the boss told me that was critical. If I do that, I'll turn off the power. I can't do that. Or he'll kill me. And we just so what are you going to do? Now you're doing the switching, and granted you want to. Let's go back and say, I don't think I want to do that. I'm going to make this a little bit smaller because you can remember the things we're looking at. And a little bit smaller. Yeah, that should work. So that was a mistake. And I'll close this bus. Still a little, yes we are. So now I got power back on. I'll get this big enough so I can see what happened. Yeah, I got power back on. I didn't make any progress with that first switching. I still think it's the right thing to do, but I killed that bus. What am I going to do to serve that little bus on the bottom? Because it's critical, and I can't turn it on. I've got to provide power to it. And that's part of my switching job. It's something very important for the plant. I don't know what, but it is critical. Can you see that one breaker here is open? Well, if I close it, then I have an alternative source of power. Isn't that why the thing is in there? Because I remember he said something about tie breakers or something. Let's close that breaker and see what happens. Well, let's look what's happening now. We've got 0.983 is the voltage level, 98%. That's a nice voltage level. And the loads look pretty decent. There's nothing there, nothing in red. I'm going to close this breaker. It simply says it's a low voltage air circuit breaker. Okay. We close it. Well, that's interesting. We get a little bit of watts going to the left and a little bit of bars going to the right. It doesn't amount to much. So that looks like it'll probably work. Let's go up here and open the breaker. Where was that breaker? It's this one over here, wasn't it? I'll open this breaker and why did it get all this red stuff? Because that didn't happen the first time I did it. That's a question. Somebody think, why did everything turn red? Well, the wires are still going. You know, the wire came from the top, went through some transformers and buses, and down to the bottom. And now and when I turned off the power, of course the power didn't go. Then I made this tie breaker, and the wires are still there, and I re-energized the bus from the bottom, from the other side, from the low voltage side. It doesn't matter where I energize it from. I cannot put my finger in that bus if I want to live a long time. So you look at it and say, well, thank God for a computer program, because I might have done that. That's bad. That isn't going to work. That's the first step. You open the top breaker. That didn't work. You didn't have power. The second step, you closed the bottom breaker. And you had power for the emergency, but that didn't work because you energized everything up toward the top. And that's how you go through all these iterations and keep track of them so you don't forget, and an hour later you're doing the same one over again because you couldn't remember if you did it. And just out of curiosity, you say, well, I wonder how well it did. Well, that held the voltage to 91%. That's not great, but, and there it's at 91%, 0.2. Yeah, the voltage is there, but I can't do that because I need to de-energize that bus. And you can see the various things, and one of the reasons the voltage is at 90 in red is because you need 90, your program said, I want 95% voltage. You don't have it, you have 92%. There's bad news all over. So you say, okay, I open the bottom breaker, or the top breaker, so I'm not going to mess with that. And you go down here and say, oh, I see. This bus is feeding up through this breaker. And that's how all the power is going up. I didn't see that the first time I looked at it. Let's open that breaker and see if it keeps things energized down below. I killed everything up above. There's zero power flow. There's no voltage there. What happened down in my little bus that I was trying to solve it? Looks like I have power. And there you are. You can say, yes, that is my switching sequence. You think, now, how am I going to do this? I had better close the bottom breaker first so I have power coming from both ends. Then open the top breaker, and then open the last one I turned to isolate the top area. And you're working with a computer program. You think, does that make sense to you? Would you be willing to do that if you were in the plant, or did you tell the boss, say, this is what we're going to do, Chief, is we're going to close the tie breaker at the bottom, make sure that important bus has power, even though it's not much, and then I'm going to open the 13.8 kV breaker so I don't get anything from the utility, and I'm going to open the 480 volt breaker at the bottom so I don't feed back, and let's not worry about all the grounding and withdrawing, and we'll do that in our usual fashion. Would you be willing to work on it that way? I'm glad to see the head shake this way. What do you think? What? You're hesitating, and there's a reason. You're not just shaking because you're falling asleep. It's because you have an idea.
So we can open that breaker near to the feeder where we can go.
That's right. Work it as close to the feeder as you can. And that's what is the switching procedure in using a computer? This system is simple enough, you could probably do it by hand. Just take a look at the long line and by observation figure it out. But we're using the computer to demonstrate how it can be done if you have a computer program that will do it faster and with more accuracy. Well, as we looked at load flow, I wonder what happened to the short circuit level, because I've got a little time now I can look at it. So I'll click on short circuit, and I'm going to go on phase A, because I've got to pick some phase, and I'm going to go three-phase fault, and they usually fault the line to ground, but I'm going to go three-phase, and let's see if it'll tell me anything. Short circuit, all buses. Okay, I have to pick a bus. I'm going to pick that bus, and okay, we have 26,000 ampere short circuit three-phase. And that's the only one we're going to calculate because we're just not going to spend time this morning. And I don't know, it's probably, maybe it's 42,000, maybe it's 25,000. If it's 25,000 ampere rating and it's at 26,000, that's a hard call because, and it's energized from both ends, you close the breaker. can you live with 26,000 on a 25,000 ampere bus? And it's a judgment call. Maybe you can and maybe you cannot. Maybe you do like the man in Alaska who said, I will live with it for the minute or 2 minutes it takes to make the transfer and gamble probability, probably it will work and I can live with that. Or you may say, this is old, this equipment is 50 years old. It was 25,000 amperes 50 years ago. I don't trust it. So the answer is, I don't know the answer. You have to decide. And you look at it and say, well, interesting that 3 kiloamps are coming from the top and 22 kiloamps are coming from the adjacent bus. I wonder what happened to the other buses. Let's pick this bus because it's close by, and it's 31,000. Okay, well, this is 25 and you're going to 31. You're going to say, well, the bus over on the left, I could live with that even though it was marginal. This one from 25 to 31, I don't know, that's 6 out of 25, that's 25% overload. The honest rating, I would be skeptical. How bad is this one? Or how good is this one? That's a 22,000. Okay, that one's all right. So you say, I have a worry about the middle one. Now it's a decision. What are you going to do? And maybe you decide you'll take your chances. Maybe you'll decide, no, we can't do it that way. We'll have to have open one breaker, close the other, and be a transition with it. For a moment, you'll have no power, and you'll have to tell the people that's, I'm sorry, that's the way it is, and you'll have to manage with it, because we can't risk blowing up the equipment. And those are all areas you say, well, what shall you do? And it's not in the book, it's in your judgment. And that's why you went to university, so that you would have this information and you could make some kind of a judgment. There we are with those are the purple ones we looked at. Here's the first one. Well, I think what I'll do is I'll close all of the breakers and then open the ones I have to. And then nobody will lose power except the ones who have to. And everyone should be happy. Okay, well, there I am. I close that breaker. And that's the bus I'm looking at. And nothing turned red. I'm okay with the top bus. You feel happy about that. Let's go down the line and see if anything else turned red. Nothing turned red there. Come down here. Let's look at this bus because I'm going to close this breaker too. There we go. That's going to make everything energized. And then I'm going to select this bus and say, what happened? I've got 40,000 amperes, 40 kiloamps. But this is what you need to know. You could calculate this by hand. How long would it take? Longer than you want. And I did this with my left hand clumsily, and it took us, 2 minutes. So now comes the judgment time. This isn't in the book. This is truly judgment, and it's your responsibility. Your answer is going to control the effect on people and on the operation of the plant. If that bus has 40,000 amps, and it's rated 42, okay, you can live with it. If you don't like it, then but it's only for a little while. If it's rated 25,000 amps, as long as nothing goes bad, it doesn't matter. So, how likely is it that something will go bad and you'll have a short circuit? And I don't know because I don't know the equipment. So that might be the point when you have to go to the plant operating people and say, that bus there, what sort of shape is it in? And if they say, well, it's in terrible shape, we've been wanting to work on it for 2 years and have never been able to, then you say, then I'm not going to trust it. If they say, oh, we just put it in 6 months ago and it went in just as smoothly as could be, you say, oh, okay, I will. And document why you did it, because somebody 2 or 3 or 5 years later will say, well, they did this switching, I wonder why. You know, they were right on the margin, and they did it, and they usually were lucky nothing happened. Was it prudent? Was it because I have to do it now 5 years hence, and I need your experience? So when you do this, say, yes, it's rated 42,000 amperes. I'm picking a number because I want the answer that way. And it's good for 40.4. I'm okay. And put a note down and say, this was installed within the past year, is in good condition, and is reasonable to, it's within limits, no problem. Someone 5 years later will be different, but at least they know that much. Now, the other thing to remember, oh, wrong button. There we go, that's all I want to show. You'll take this, here's your switching operation. So you decided how you're going to switch. You will open certain breakers, you will take certain risks, or you will not. But you reach a conclusion and say, and this is the procedure. They will do this 1, 2, 3, 4, 5, and a whole list of them, and a checklist. Then if there's another engineer on staff, you ask them, please look at this and see if it makes sense. Tell me if I made a mistake. And other engineer will review it and ask you some questions. And you need that. You need that if you can get it. If you can't get it, you can't get it. You just go home and go to sleep and come back the next day and look at it and see if you can see flaws. Look for trouble in your program. Look for mistakes or risks or vulnerable points. I moved from the engineering office to a plant, a mill. I was the first electrical engineer there, and the load at the time was about 30 megawatts, something like that. And it was a new mill, and well designed, and well maintained and well operated. And I had to make the changes in the field. You know, things come up, that's why they hired me. And the hardest time I had was to check my own work, even on something very simple. You do it, and you think you have everything right, and your problem says, I don't want to make a mistake and have electricians laugh at me. But and I'll say almost inevitably, when the work went in, somebody would say, there's a little mistake here, or there's a poor judgment. I couldn't see it. And you do need somebody, I need somebody to check. If you're better than that, that's wonderful. But anyway, you take the one line here, and a single line, and you take it to the operating people, and you say, we're only going to work on this part of the system. So, that's what we're going to work on today. And, well, I shouldn't have dropped that off, should I? And you say, well, you know the rest of the one line, the single line, you know the system, and that in green is what we're going to work on. And you focus on that. Don't worry, folks, about the rest of the system. We're not going to touch it. But we're going to work on that part. And then you go through step by step by step, or maybe you want to include a little, say there's another group we're going to have. A different crew is going to work on that little piece because we found out we had to do some switching. So now you have two groups of people working. One is working on the, I'll say the higher voltage, and one's working on the critical supply, and you have to work with both of them, and you need checklists and instructions for both of them. You can't be in two places at once. So you have to take each crew and say, group number one, we're going through the critical loads. This is what we're going to do. These are critical loads. Remember, folks, that this is the nature of the process, and do you understand and make sure. And when you do have one person in charge. Don't have two, because I will think it's like two people trying to, you've done that. Somebody can't get the program up on the computer and somebody else puts their hand in to help and everything goes bad, like I did just a minute ago. So when you have a program and say, this is the program and you are in charge, if anybody wants to make a change or do something, they come to you and you document it or whatever and get permission. And the same with the upper part of it, you are in charge and you have a procedure. If anybody wants to do something or problems come up, they speak to you. And both of you, I am in charge because I'm the electrical engineer and I'm responsible for this whole thing. It's on my shoulders to do it right. If either of you see a problem, you come to me and my answer is final. And I hope it's right. And it's dangerous. You think, well, we set up at the top there, we wanted a 269 kV transformers down to 13.8 and 20 MVA. Well, 20 is not like that. 20 MVA is 20,000 kVA. And that's 20 million volt amps. So we have two of them. And I'll just stay with one half. There's 20 million volt amps. And I don't know what that comes out when you calculate with impedance. That's a tremendous amount of energy. It's 20 million tea kettles of 1 kilowatt each. So that's what you're switching. You may only turn on the light bulb. You know that story. You may only use a teeny bit of it, but the hazard, the risk is huge. And that's why you have to be careful. And you need to document this. Now, how do you document it? Well, the first thing is to take your original one line, the bad one line that you got, and keep that in file and say this is the November 6th one line that we got, existing conditions. And then you revise it and you say this is the November 8th one line when I corrected a bunch of things, have a note saying, and there are some things that I need to look at. And they're in the permanent record. When you come along and where the two purple buses were, and you said this was the switching we did in a new one line on file, and say this is the switching and all the story that we did on November 9th. And keep that for posterity, because you may want to come back. Who knows? You may want to come back and say, what did we do in that day in November? And everything went well, and I can't remember. And you can pull it up and say, then you come along and say, and here's the two that were kind of tricky. They did not go as well as I wished, and they were not as easy as I wished, and that was the November 12th one line. So that you can go back a year from now and I say, remember when I first started this job, and we had a bad one line and I fixed it, and we did some switching, and everything becomes vague, and you can recall it. Also, suppose you have to do this again next year or 2 years from now or at some time in the future. You can pull up the old one line and say, this is what we did the last time and it worked. Let me look at it and see if we want to do it that way again. And that's experience. Well, does that give you any feel for how you do switching? Does that point out that you're working with people, which is probably as critical as working with the system? It's hard to work with people. And some people, some people are easy to work with, some are not. Some have good days, some have bad days. Sometimes you get new people in because you've got a contract or you didn't have enough people to help you. So the contractor came in with somebody whom you've never seen in your life, and who's never been in your plant, and you're thinking, I'm going to have him working on a system with, let's say, 20 million watts, and those are the decisions you have to make in an operating plant. Suppose that you're in the head office, in the engineering office, and this plant is in some remote location, And you will not be going out in the plant and talking to the electrician. And that's not unusual. You're a consultant, or for some reason, you're not going to go and supervise the job personally, or they choose not to have you do that, or for some reason. Now you're sitting in the office, and you will never, well, you will not see the switching being done. You will not be there to control it. Now what do? Well, you still have to go through the same procedure. We know that we have to get those 2 buses on this side, or whatever the problem is, and you have to document it and define it accurately, saying the problem is we have to work on those particular 2 buses. Number 2, we have to keep the power going to that bottom left bus because it's critical. And explain why it is critical if you know. It's an important part of the operation. And this is how we're going to do it. First, we'll close this breaker and provide power, or whatever it is, because we need power. And caution, this will be right up at the limit of the short circuit capacity or load flow or whatever it is. So be cautious, or maybe it's beyond it. So don't stand in front of the breaker and do it. Find a way to do it remotely, or whatever it works. And go through in more detail. If you were there, you remember a lot of things that you don't have to write down. Maybe you should, but you don't have to. If you are not there, then you must list everything, because some person out in the field is relying on you. You've got this document that says this is how we're going to do this switching, and an engineer went through it carefully, and an engineer with a good reputation, so I feel comfortable. What did she say? And you go down, and you really understand what this engineer said. She said, and open the breaker, and I'm thinking, she didn't put in which number breaker. Which breaker does she mean? Did she mean the one there, or was she thinking of the one there? And those are the little mistakes that I made. And I don't know about you, but you see it, you know exactly which breaker you want. It's the one in the top left. And I don't write it down because I know it's the one on the top left. Why should I? But some poor person who's getting it doesn't know that that's the one it is. So the documentation is critical. Making sure you're very, very thorough is critical. Have confidence in yourself. Don't think yourself incompetent, even if you've never done switching before. You have a logical mind. You can do the calculations, and you are dedicated. You're doing this because you're competent, and you're doing it for your own self-respect, and it's an honorable job. Planning switching is not the most exotic thing in electrical engineering, but it's very important, and you're protecting people's lives and property and jobs. If you ruin the plant, nobody gets killed, nobody has a job, and nobody has a paycheck. So those are the factors. And the other thing, the task itself may not be the most exciting job that you've ever seen, but it's an important job. It's significant. It's a contribution to the operation and to your fellow workers. So, and that warrants close attention. And you will give it. So, of course, you'll be careful, but don't think that don't hesitate to tackle something like this. What would you do if you got along so far and said, I can't make it work? You know, I'm looking at this bus here, and no matter what I do, and I can get down here, everything seems to go wrong. And I can't figure it out. And you really can't. You really tried, and that piece will not work. And that can happen. And that's another. What do you do if you can't do the switching and what you're supposed to? What would you do if I said, okay, this is switching, come back in a week and tell me about it. And at the end of a week, you can't make it work. It just, it won't work. What did you do? And that's, this is a test. What did you do if you were stuck with that? And let's assume that I'm reasonably reasonable. I'm not completely wild. At least I've held a job for 15 years. And here you are, and you have to tell me it won't work. That I asked you to figure out the switching, and you didn't do it. Because you couldn't do it. You tried. What are you going to say? What are you going to do? It all depends. There is no answer. I think what you have to do, and this is what I would expect, is that's a beautiful sight. I think you have to go to your supervisor and say, I tried to do this, and I can't find a safe way or satisfactory way to do the switching. I can't make it work. And of course the question would be, well, why? What's wrong? And then you can go through and say, well, I opened the top breaker, but I killed the emergency bus. I closed the emergency bus, and I energized the top. Or whatever the problem was, and the only way I can see is to de-energize the emergency bus, and you don't like that, that's not permitted. Or operate with the bus energized, well, that's crazy, you can't do that. So what shall I do? Well, then it's the next level up to say, check you and say, you're correct. Your analysis is correct, that the switching task you were given and the constraints that you have to work within are not possible. It won't work. So, and you've approached the solution. You said, forget the emergency bus, and I can do the switching. And maybe that's the only option that either of you can see. Then it's his job to go to management and say, we have to do the switching. We'll have to do something about the emergency bus. And the question may be, well, what shall we do? And I don't know, maybe you live with it, maybe you get in a standby generator. Then you solve that second problem. But it's your responsibility to tell management what they need to know. Don't withhold any information. Tell them that this is risky. We may shut down the plant, and we may not. I don't think we will, because the odds are pretty good, but there's no guarantee. They need to know that, because how else can they judge? They know less than you do, because they know only what you tell them. It's, I guess the whole question of switching is a people-to-people problem, supported by technical knowledge, because technically you can figure it out. And you have to work with the people who are involved in the actual switching. I'm going to stop there for the moment, because Satish said I went on too long with this, so I said last week, and I don't want to do that again. But what do you people think? What comments do you have, or what questions, or because you're an experienced engineer. So you're a young engineer, you're an experienced engineer, you're not novices, and you do have good ideas. You know it. If somebody breaks the ice, then everybody else will have a question. I'm going to, yes, I'm getting all my family here. That's why I have it as background pictures. I like it. That's why I need to shop for bangles before I go home. So now you know. Whether you say yes or no, was it worthwhile to spend a morning in this? Did that give you any insights that might prove of interest or value? Because what you tell me, I'm going to remember for the next time I present this, so that I hope it will be a little better each time. I'm going to mention a couple other things. So we do have a few minutes, do we not? Okay, good.
Like you do some of the other features of particular software is.
Okay. Oh, yes. Save changes. No. 1,500 miles away, and these people are 300 miles away. So it makes a difference. And I find this a very easy program. It tolerates my level of ability. I can enter data and make mistakes and correct them, and it's not hard. I find ETAP a little more difficult. It's a very good program, don't get me wrong. ETAP has the advantage that it's certified for things like nuclear applications, because the nuclear people are very fussy and want to be sure that whatever you do has been certified that it will really, really work. Easy Power chose not to go that way. They're just not interested in that market. So there are some differences. ETAP decided they would have a switching program. You can buy a load flow program. You can buy a short circuit program. You can buy a bunch of stability. And you can buy switching. And the switching program, I talked to Farouk Shakur, it's his company, less than a year ago, and he said that developing the switching program, the software, took 3 man-years, 6,000 hours of work. And I believe it, because software is not easy, and that was based on integrating it into his existing system. And he said, we have more work to do. It's a functioning system, and I'm sure he's done it by now. But it's a tremendous effort to do the software. Easy Power said, if you're willing to look at it step by step by step, and it's not a huge system, so you can do that, then you can use the existing programs. You don't have to buy another $3,000 program. And I prefer that because I like to go step by step because I'm cautious. I want to know what's happening. And that's me. And there are several other programs available. SKM is one of the earlier ones. And I don't know why they're not interested. We had a working group, and ETAP and Easy Power both participated and contributed. And when we presented this program, it's been a year ago, May, in California, and their office was right there at an Ieee-Ias meeting, and they attended the meeting, and they had an exhibit and showed their things, and I walked over to them and I said, aren't you interested in the switching work I'm doing? And they basically said, what switching work? I said, well, we have a report in Detroit on this stuff. And they said, no, we're not. Something was wrong with the office. It's not wrong with the company, I don't think. But the lady who was in charge was running around trying to run her booth, and she had a young man with her, and they're both very good. And somehow they sent him from the office without any business cards. And I think what happened, things go wrong. I think something happened in their office, and they said, we forgot, you've got to be down there this morning. And so they never did participate. But you could use, even if they hadn't, you could use the same procedure with the care software. Now the things that are available here, let me get a start program. I can figure that out. It will start. And I do not want to bring my stability study up to date while we're standing here. There's one of the programs they have is stability. So if you want to know, we had 2 generators on this bus. We had a little one at 2300 volts or something, then a big one at 13.8 kV. If you lose the utility supply, is the system stable? Will it pick it up? How quickly will it respond? And I don't have that data either. But if you have a generator, you enter that data. So you can figure the stability harmonics. I'm keeping away from harmonic. You need the third harmonic. Maybe there are other harmonics. And we have some adjustable frequency drives there, and they're just known problems with the harmonics. You generate harmonics, come back in the system with I saw one number that 2/3 of the harmonics are generated when you have a problem, are generated within the system, and 1/3 come outside. I think most of them are generated within the system. Power flow, let's look at power flow. you can get the, you're going to solve it. Okay, you can look at that one. It'll display the voltages on power flow. It'll display the generators. It'll give you the motor and load data. It will give you different branch flows and transformer taps if you need to do it. And then you can go with power flow. You've got power factor options. If the power factor is bad, and it is bad in this because I have no power factor correction. Maybe I should have capacitor. Maybe. Anyway, you can calculate that. You can text reports and a whole bunch of other things. Short circuit we looked at, and it'll give you whether you want the short circuit from phase A or phase B or phase C or three-phase or line to ground or line to line or what's this one? Line to line, this is 2 lines to ground. So you can, whichever analysis you want, they're there. Also, short circuit generates arc flash, and without getting into that, there are a couple of ways getting injured electrically. One is you get both things, and the current goes through your heart, and your heart starts to flutter or does bad things, and or maybe you get burns where the current enters and left your body, and you get deep burns. Another thing is the arc flash. You may not touch it, but if you have tremendous, well, say it's just a small arc, 2,000 amps, 2,000 squared times T. I squared T is a number. It's the measure of the energy that's involved. And you have that in something the size of this podium here, and you have all of a sudden that energy there. The other thing, what is it when water vaporizes? I think 1 milliliter becomes 1,800 or 18,000 milliliters. 18,000, I think it is. Steam is much bigger than water. If you vaporize copper, what you do, it goes from 1 to something like 89,000. So there's a tremendous burst of energy of impact or shock wave, I was calculating one time, because somebody said this is dangerous, and I thought, it's not that dangerous, I haven't worked yet. But I thought if I stand this far away, which is 40, 50 centimeters from the panel, and there's this sudden arc of, I figured 1,000 ampere is it's an easy number to work with. But the force in my body, and I thought, well, I'm not that big, so it's a small area, was several hundred pounds. And I thought if I were playing football and somebody weighing several hundred pounds hit me, and that was with a small arc, so there's the pressure from that. There's the energy from the heat, because the heat of an arc, as you're thinking of the surface of the sun or more, it's a tremendous amount of energy. And they talk about personal protective equipment for clothing to protect you from the arc, from the energy of the arc. And that sounds very good. But what they say is that if you have, they stop at 40 calories per centimeter, because beyond that, it's just outrageous. But even at the lower levels, 5 or 10 calories per square centimeter, the definition of the arc flash protection is if I'm wearing a shirt, if this shirt is worth 10, whatever the cost is, 10 calories per square centimeter. What that means is that if I'm exposed to that, inside I will only get a slight burn. It does not mean that I will not get burned. And it also means that if I'm wearing something flammable inside, under certain circumstances, it may be that the arc is okay on the inside, but my shirt underneath is starting to burn. Well, that isn't something that is very good for you. And they neglect the hands. They say, well, we're not counting hands. The hands are right up there, because you should be wearing gloves or something, so hands aren't in the measurement. So personal protective equipment is not perfect by any means. And the other thing is, if you're wearing personal, so they put me in some kind of a suit, so I'll be protected from the arc, and it works. Now in this climate outside, and I'm supposed to be doing something with a screwdriver or whatever, it's hot. I can't work for very long. I'll be steaming in there. I'll cook. So there are limitations, and that's one of the reasons for calculating this. We did not go into the arc fashion all of it. We only looked at load flow because it's easy. So we peaked at short circuit. But we didn't do the rest of it because we didn't have time. But when you're doing your analysis, you want to say, I know what the short circuit is, and we were comfortable with 42,000 amps or whatever it was. That may have been a very bad decision, because maybe 42,000 amperes were 60 calories per square centimeter. We never looked at that, we never calculated. So you have to go through all of the calculations we neglected and record them and track of it. It's a big field, and you need all the support you can get. And I'm a firm believer in using it in software. Software is not free, it's not cheap. And what do you do if you're working for Tata? You say, well, you can sell another ton of steel and buy the software. If you're working for a smaller firm, maybe they can't afford it, or maybe they think they can't afford it. Then what do? I think the approach is to either find a consultant who has the program, who's spent the money and pay him. And that's what I'm doing on a project now. I talked to a friend of mine, I said, as soon as I get back from India, we need to sit down and talk, because I have a small program I want to calculate. I am not going to buy the software, I'm not going to do it. But I want to know if you can do it, how well qualified are you, and how will we go about it, and what will you charge? And they have the software, so we don't have to spend $18,000, and then we'll reach an agreement. And I know we can do it, we just have to settle it. So maybe the answer is to go to somebody, find out if the system is on somebody's software, say they picked SKM, then go to somebody who handles SKM, or who is willing to, and say, will you do this for me, and in some timely manner, and what will you do, and this is what I want in the way of switching instructions. This is what you will tell them what you want and when you want it, and pay them for it. So that's, instead of paying $18,000 plus your effort, you pay for the effort. So that's another approach. What do you do when you don't have the software? Can you find a source for the software to do the work for you or with you? Well, it's different. Maybe you'll ask. You had a comment? No. I was watching. So it's a hard question, and we're going through that. What do we have? Did I say they have stability? Did I mention that? Harmonics? Yes, I did. And there are different ways you can manipulate all this information. Now, the other thing they have in this program, and so does CPAP, is suppose you have direct current buses. You have a running aluminum chemical plant or something, but you're using DC. The AC system doesn't work for DC. However, they do have DC programs in their program so you can work DC functions. The problem that the software vendors have is getting equipment data. If this breaker is a DC breaker rated 600 amps at 600 volts, how much will it interrupt? And will it interrupt in a second or a cycle? And so on. The data is very sparse from the manufacturer. It's improving, but it's a question, you don't have the information to put on a single line, or you have limited information to put on a single line. But whatever's available in the market is there. If it's not available in the market, it's not there. It is coming. So what else can we do with this? You can program in various alarms. So, if you say on this particular bus, under these circumstances, I want an alarm. The opportunity it opens is suppose that you are fortunate enough to have this. Where's this? Oh, there we go. Yeah. Yes, sir.
So in India, we are having different type of circuit breakers or different type of switching arrangements present in our power system. You said here that the perfect regulation of switches are important for the regulation of the power system. So we are here having the electronic switches some places. We are having electromechanical switches at other places. We are having mechanical switches. So, sir, I want to know a proposal from your side, sir, how we regulate all these different type of switches, because everything is having a different operating conditions, different operating times. So how we regulate all these switches in our power system to maintain the regulation of our power system?
And how do you regulate when everything is different and everything is valid? That is a difficult task, of course, or you wouldn't have asked. But actually, with anybody's software, you can enter in for each piece of equipment how it performed, whether it takes 3 cycles to open or 7 cycles, and whether the relay coordinates an electronic relay that does something wonderful, or an old induction disc that works or used to work, and you get all that data into your database, which is crucial on the single line, and all. I didn't go into the backup data. You can enter all of your information, and that you need to put in as well. Then you can say, under these circumstances, with these components, this is how they perform, what will happen? And it'll calculate, whatever you told it, it'll calculate. This happens. And you decide, is this tolerable or not tolerable? And then it's a decision time. If it's tolerable, okay. If it's not tolerable, then you look at it, and I look at it usually just by observation, and look at it and say, this portion of whatever equipment we have in this portion of the circuit is not tolerable. What can I do? And maybe you change the operating parameters, or the relay settings, or you look at it and see which variables can I control. And you adjust them as best you can and try again and say, is this better? And if it's better, you're gratified. If it's not better, you try something else. It's hard. You have to have all of the data of your equipment so you know exactly how it will perform. You have to bear in mind that as the equipment gets old, it may not perform despite what the manufacturer says. And that again is a judgment call. And one way you can do that, if you talk to your associates and your peers and say, what experience have you had? You have this particular kind of switch and operating controls, and I have something somewhat similar, and I have a problem, or I expect a problem. What have you done? And the communication back and forth, you get 3 or 4 people, and pretty soon you have an answer, or maybe the answer is not what you like, but that's what it is. Did I answer your question? Not really? Well, maybe you should answer the question, and I'd be very happy if you would have explained your position. What do you think should be done? I'm going to turn this thing off because we're not playing with it anymore, and you see my bandwidth. There we go. Okay. Then if we need it, we've got it. The problems we run into, the people have no easy answers, but what would be your approach to the situation like this?
So anyway, all switches having the low operating time, other than the mechanical and electromechanical. So we will set the preferences according to that.
Yeah.
For mechanical, we will take.
But would you have a microphone because the other people want to hear it too? Tell them again so you can lecture to us.
I'm not sure about the answer.
Well, that's all right. We're not keeping notes.
within my perimeter is my wild guess. It's mechanical switches that takes, it needs a manual operation.
Yes.
As well as it takes more time for breaking that circuit if it is a mechanical circuit breaker. When in electromechanical, comparatively less time, it can be made sophisticated as well as manual. And the sophisticated switches, it is only working over the programs and all. And we can control it from sitting at one place through our computers. And
Yes. Yeah.
so we will set the preferences according to that. Like mechanical switches, it is to be operated manually, take more time. So we had to set the preference in such a way that first of all we had to operate on that switch. Afterwards electromechanical, afterwards soft switches.
Yeah.
It's my guess. I don't know if it's a hit.
Well, it's certainly reasonable. I would try it. I would be comfortable. Yeah.
Only one more question. We are running out of time.
So suppose I have opened a breaker that which is the wrong one.
Yes.
And there will be some problems in the power system.
Yes.
And what I have to do to restore the system parameters, the system operating condition, even though I have opened a wrong switch.
Yeah. And that happens. The wrong switch opened, or the name on it was wrong. It said A, it was really B. And these things happen. That's where you have to think fast. You have to say, it's the wrong one. If I open it, I should close it. Maybe you shouldn't. Maybe because you have to think, now, what am I closing? Suppose it's just big motors, and you open the wrong big motors, and you know this is a bad situation. The motors have some energy because the flux is still decaying. If you suddenly close it, maybe you close it out of phase, and you're going to have some terrible currents. So maybe you need to wait until the flux decays. Picking that as an example, it's a hard question, and my inclination is to close it right away, and that is not always wise. I think the prudent thing is to say, well, I opened the wrong switch, and I'll wait until all the energy decays and things are stable, and then I'll bring the system up again. Maybe you have to bring up one motor at a time. And it's difficult. It's bad for the plant. And then you have to go back to your single line and correct it. Usually it's something that was labeled wrong. The nameplate said one thing, but the function was something else. So they didn't change the nameplate or the pet peeve of mine is they'll name equipment surge pump number 1. Opening the wrong breaker is not unusual. Or closing the wrong breaker is not very. It's a very valid and reasonable question, and it's a difficult one. I don't have a good answer. You suffer through it. And I guess my answer, if I were faced with it, my first inclination would be to close it, but don't do it. And my next inclination is wait until things are stable, and I know what I'm doing, and then bring the system up again. But management doesn't like that. They want the power.
Thank you, sir, for that exceptional talk. Now I request our HOD, Dr. Chandramohan, sir, to present a memento to the chief guest as a token of appreciation.
Well, thank you very much. Thank you very much. This is really a privilege, and you know I would talk all day if you would tolerate it. And show you the family too. Thank you very much for inviting me here.
Respected Chief Guest, Mr. Erling, Hesla, HOD, Dr. Chandramohan sir, teachers and my dear friends. We had a valuable talk which really stand in good stead in our academic and professional life. I'm sure that people who have gathered here have had a wonderful experience. co-generation, Mr. Erling Hesla, who has come all his way from US to impart valuable knowledge in the area of power system switching. Is really a blessing to us. I also got a rare chance to be with him for 2 days to take him for his houseboat cruise in Kumaradam. So that time also was very generous and also shared so many experiences he had faced during his 50 odd years of professional life. So as my role is to extend a vote of thanks to this lovable and great person, I on behalf of Ieee-Ias Students Branch Chapter would like to express a heartfelt thanks to you. Thank you, sir. Now, I also would like to express my heartfelt thanks to the HOD of the Triple Department, Dr. Chandramohan Nayak sir, whose guidance and spirit helped to make this event a great success. I would also like to thank Dr. Shankar sir, Principal, and Bijukumar ji for the full support to make this event success. So I would like to mention a special thanks to our advisor, Mr. Srikanth sir, whose all-round support have made this event a great success. So I would also like to thank the ICTS and the service for the support they have extended throughout this event. I would like to thank all the staff members, teachers for their valuable support. Thank you.